Welcome learners. I am Dr. T. Gangaram, lecturer in statistics, SVA Government College, Srikalahasti. In this video lecture, we will discuss joint distributions, a geometrical and conceptual approach. Here, why do we need two random variables? In real life situation, particularly in pharmacy company, wants to study the quality of its tablets. First, only one tablet weight is recorded. Tablet 1 to tablet 4. First tablet weight is 495 milligrams. Similarly, for tablet 2, 503, it is 498, it is 501. Only one characteristic is observed here. Here, the weight and dissolution time are recorded. For the same set of weights also, the time of dissolution. For tablet 1, the weight is 495, whereas the time is 8. Similarly, for 503, time is 10. For 498, time 9. For 501, time 7. Here, we observed for same tablet, two characteristics. One is weight and the second one is time. Here, two characteristics are observed simultaneously. Whenever two random variables are observed together, their behavior is described as joint distribution, joint occurrence of that event. Why do pharmaceutical scientists study two variables together? Many important pharmaceutical decisions depend on the relationship between two characteristics measured on the same tablet, same patient, or same medicine. Here, let us look at one example: tablet weight, dissolution time, dose administered, drug concentration, patient age, blood pressure, storage time, drug potency, temperature, drug stability. These are the examples for two variable cases. We need to study two variables at a time. This is called joint distribution, or the probability of the joint occurrence of two variables simultaneously is called joint probability distribution or joint probability function. A joint distribution describes the probability behavior of two random variables observed simultaneously. One random variable to two random variables. In one random variable, only one characteristic is measured, like tablet weight. Here, the possible observations are from 490 to 510. Here, we observed the average weight of this tablet, uh, dispersion weight, like that. Similarly, if two characteristics are measured, here the first variable is taken as x and second variable is weight. Here the weight and dissolution time we take. The possible observations in our previous example: 495 8 minutes, 500 8, 503 10, like that. Here the diagrammatical representation of two variables is two variable plane. The weight and weight is taken as x-axis and time is taken as y-axis, like that. Here a single random variable is represented in a number line, whereas two random variables are represented as points in a two-dimensional plane. This is single line. Here we need two-dimensional plane to represent two random variables or to observe two characteristics simultaneously at a time. Here, the definition of random variable, joint random variable, is it consists of two random variables observed simultaneously on the same experimental unit. It is denoted by x comma y, where x denotes first random variable and y denotes second random variable. This is the example of 5 tablets are selected randomly, tablet 1 to tablet 5. These are the possible x values. Each row represent one set of random variable. joint random variable x comma y. Here, this is the diagrammatical representation, geometrical representation of two random variables. This point gives us 495. This points another point. These are the five different points gives us five joint random variables. Every tablet is represented by one point. In the two-dimensional plane, the collection of all such points form the basis for giant probability distribution, similar to univariate probability distribution. Our motivation here is, after collecting many observations of x comma y, we would like to answer the question, which combination of x and y are more likely to occur? What is the possibility, what is the probability of occurrence of giant random variable? To describe this mathematically, we use giant probability density function known as giant PDF. Here giant PDF is denoted by probability f of x comma y. Here x represents first random variable, y represents second random variable. F of xy measures the probability density at the point x comma y. This x comma y gives us the point, whereas f of xy gives us the measure of probability at that particular point. Unlike a one dimensional random variable, the giant PDF describes probability over a two-dimensional region. Here, this is f of xy gives us the probability of occurrence of that event jointly. The giant PDF describes the probability behavior of two random variables simultaneously, whereas one variable we denote it as f of xy, two variables f of x comma y. The properties are similar to univariate. A valid giant probability density function must be satisfy the following conditions. It must be positive always, since probability can never be negative. It is a positive quantity for every point of x comma y. F of xy must be greater than or equal to 0. No point is a negative, takes negative value. Total probability must be equal to 1. Here R is the region. We call it as support region or region of the points x comma y over which the density is defined. Here this is the region. This is the possible region of occurrence of joint random variables x comma y. We call it as support region. The key observation is, the probability contained in the entire support region must be equal to 1. Just as the total probability under one-dimensional density curve is equal to 1, the total probability over two-dimensional support region also equal to 1. Think before we define. Suppose the random variables represent x is tablet weight, y is dissolution time. Can every point in xy plane represent a possible observation? Here, the possible observations, tablet weight cannot be negative. It must be a positive quantity always. The time also never negative. Dissolution time cannot be negative. Only some combinations of xy are physically possible. Not all possible. All combinations are physically possible. Probability exists only inside the allowed region of the range of x comma y. Here, this is the support region, and whenever a point occurred outside the support region, that is an impossible event. Here, the region where f of x comma y is greater than 0 is called support region, or the giant probability of the giant probability density function. Outside the region, it must be equal to 0. Here, different types of support regions are: the support of a giant probability density function is the region where it must be greater than or equal to 1. Here, the shape of support depends on the conditions given in the problem. If conditions of x and y are, if x is less than or equal to 0 to 1. The range is between 0 to A or 0 to B. The region is like this. This is the square type region. Whereas if 0 less than y less than x less than 1, if y is less than x, then the region should be in the triangular shape. Whereas if these both are equal, it is a rectangular region. In case the circular type regions also come, whereas the variables have squared quantities. Here, if one variable is in squared quantity, the curved region also occur like this. This is the support regions. We have four different types we can define: square type, triangle type, circular type, and curved regions. Before solving any problem involving a joint PDF, you must remember, draw the support region first, then the limits of integration become obvious after drawing the region. Here, to draw a support region, we follow the four-step procedure. Whenever a joint probability density function is given, follow these four simple steps before performing any integration. Read the inequalities carefully. Suppose, for example, 0 less than or equal to y less than or equal to x less than or equal to 1. This must be a triangular region. Draw the boundary lines of the curves. If x is equal to 0, for y is equal to 1, x is equal to 1, y is equal to x, we need to draw boundary lines or curves carefully. Identify the feasible region. First, shade only the region satisfying both the inequalities on the variables. Write the limits of the integration. These limits are obtained directly from the shaded region. Here, this is the triangular shape. Here, y is equal to x. For this, 0 less than or equal to y less than or equal to x less than or equal to 1. For this type of conditions involved in the joint PDF, we need to draw the support region like this. First, draw first the region, then integrate. Never write the limits of integration without drawing the support region. For example, the joint probability density function is given by f of x is equal to xy by 1250. Here the range of x is clearly defined. The x is 0 to 10, between 0 to 10, and the range of y is also between 0 to 10. That means the x cannot take beyond 10 and y cannot take beyond 10. Outside the region, the f of xy must be equal to 0. The given conditions imply x is between 0 to 10 and y is between 0 to 10. That means x varies from 0 to 10 and y varies from 0 to 10. The support region is a squared type region. Here the value of y is 10 here and the value of x is 10 here. Our all probabilities must be lies between these shaded green area support region. Since the density is positive only, inside the square, all probability calculations must be performed within support region. Let us solve one problem. The joint probability density function is given by f of xy is equal to xy by 1250. This is the range of x between 0 to 10 and 0 to 10, and find probability of curve. You need to find the probability to be calculated carefully. Probability of x less than or equal to probability of 2 less than or equal to x minus y less than or equal to 3. The probability statement contains, here we have two inequalities. This xy must be greater than or equal to 2. The 2 is the minimum boundary for the x minus y. So we can write x minus y greater than or equal to 2, and it must be less than or equal to 3. We can write x minus y less than or equal to 3. These two conditions involved in our problem. So we need to find the probability such that these two conditions must be satisfied. We need to draw the possible the region first. Here this corresponds to two straight lines. The inequality we need to transform. To draw the shaded area, we need to transform these straight lines, the inequalities into equalities. From this inequality x minus y is equal to 2 is the straight line, x minus y is equal to 3 is the straight line. The required probability is the region lying between these two lines. Here I draw these two lines. Here first the blue shaded area is satisfies x minus y is equal to 2, and this red shaded area is x minus y is equal to 3. So before evaluating any double integral, always convert the probability statements into a geometrical region. We converted the probability statements into a geometric region. The shading the required probability region is first probability statement is probability of 2 less than or equal to x minus y less than or equal to 3. The inequalities become equalities x minus y is equal to 2 and x minus y is equal to 3 form two parallel straight lines. First to draw the support region 0 less than or equal to x less than or equal to 10, y less than or 0 less than or equal to y less than or equal to 10. Draw the two boundary lines x minus y is equal to 2 and x minus y is equal to 3. Here, shade only the strip satisfying the conditions 2 less than or equal to x minus y less than or equal to 3. This must be between 2 and 3, and x minus y is equal to 2 and x minus y is equal to 3. For we need to draw a straight line, we need 2 points. Suppose in the from the first equation put y is equal to 0 here, then directly we get x is equal to 2. Then the first starting point is 0 to 0 comma 2. Here this is our first starting point, 0 comma 2. Here we need the next point, this point. How can we get that point? Here put y is equal to 0, put y is equal to 0, then x is equal to 3 from this here. Put y is equal to 0, x is equal to 3. So we have starting points are 0 comma 2 and 0 comma 3. This is for the first line, blue line. This is for the second line, red line. Similarly, the ending points, put x is equal to 0, 10, then y is equal to 8. Here put x is equal to 10, then y is equal to 10 minus 2, that becomes 8. So the ending point at 0 comma 2 is 10 comma 8, and put x is equal to 10, then y is equal to 7. That means 10 minus 3 is equal to 7. 10 comma 7 are the points of our shading. Here look, here this is y is equal to 0, x is equal to 2 here, and similarly for x is equal to uh, what is the value, x 10. Here x is equal to 10 and y is equal to 8 here. Here this is 7. Draw a straight line here. These are 1 2 3 4 5 6 7 here and 8 here, like that. This is the 10 value. So we need 2 points to draw a straight line. So the first point for blue line is 0 comma 2. The last point for x minus y is equal to 2 is 10 comma 8. Similarly for this point x is equal to 3 and y is equal to 0. So 3 comma 0 is the starting point, and for x is equal to 10, y is equal to 7 here. These are the points. In this way we need to draw two straight lines. This yellow region is our required probability. We need to find this area. For that we use integration. The required probability is simply the total probability contained in the shaded strip. The next step is to express the shaded region as limits of double integration. Here this is the shaded strip. How do we convert this region into limits of integration? Here, the vertical strips. Choose a vertical strip for every fixed value of x comma y changes from y is equal to x minus 3 to y is equal to x minus 2. Suppose substitute x is equal to 5 here. Here 5 minus 3 gives us the value 2. Here substitute x is equal to 5. 5 minus 3 gives us 3. So this is the minimum of variable y, and this is the maximum of y. So y varies from x minus 3 to x minus 2. So the range of y is decided as x minus 3 to x minus 2, where it comes from here the given region. Everywhere you can get from this also. Here y is equal to x minus 3. From this equation y is equal to x minus 2. So this is the region for y, and we can decide the range of x here. This is 3 to 10. I have given a detailed explanation for the finding of lower limit x is equal to 3. Here the strip is bounded at bottom by the line x minus y is equal to 3, which can be rewritten as, since our support region is a square where y cannot be negative, such that the lower possible point of this line occurs right on the x-axis where x is equal to 0. Substitute where y is equal to 0. Substituting y is equal to 0 into the line equation. Suppose if we substitute x is equal to, if we choose any value of x lies less than x less than 3. Suppose we have taken, if x is less than 3, for example x is equal to 2.5, then the lower limit for y x minus 3 is equal to minus 0.5 becomes negative, which which falls completely outside the valid region. So therefore the region where y varies perfectly from the lower line y is equal to x minus y to the upper line y is equal to x minus 2 strictly precisely starts precisely at x is equal to 3 only. Any other value does not gives us a positive value. So the lower limit for x value is 3. We decide like this. Finding the upper limit x is equal to 10. As you move your vertical strip to the right, the shaded strip continues uninterrupted until it hits the absolute rightmost boundary of the square support region. According to the given problem statement, the maximum boundary for the variable x is explicitly restricted to 10 only. So the vertical strips covers the entire span x is equal to 3 to x is equal to 10 on the right. Here outer limits of x, look at the absolute minimum and maximum horizontal coordinates where your vertical strip can slide from left to right, that is 10 to 3 to 10. The inner limit of y, look at the bottom boundary and top boundary at the vertical strip touches at any given position x minus 3 to x minus 2. This is the condition. Here this is the area of x. Here x is equal to 3 here and x is equal to 10 here. We need to find between these two lines only. This is the area of limit of x. This is the area. So golden rule is, choose one strip, keep one variable fixed, read the lower and upper limits directly from the graph. You can decide the limits of coordinate x and y. From the shaded region, we observe that x is 3 to 10 and y is x minus 3 to x minus 2. So the required probability is obtained by integrating the joint PDF over the shaded region over the limits of given x and y. Therefore, probability of 2 less than or equal to x minus y less than or equal to 3 is, the range of x is 0 to 10 and the range of y is equal to x minus 3 to x minus 2. The given function is, joint probability function is xy by 1250 dy dx. Here this is the probability required region. This is dA, where A is the required region of the support. Here this is the green area of integration we need to find. The same probability can be evaluated in another way also by using horizontal strips. For a fixed value of y, x varies from x is equal to y plus 2 to x is equal to y plus 3. The value of y varies from 0 to 7. Hence, the range of y is 0 to 7, and it is the opposite. Here we fixed x and find the range of y. Y plus 2 less than or equal to x less than or equal to y plus 3. Here, this is the area. From horizontal strips, we can find both ways we can get the same answer. This is x is equal to y plus 2. Here x is equal to y plus 3. The horizontal strip keeps y fixed and allows x to vary. Writing the double integral using horizontal strips, it is 0 to 7 the range of y is, and the range of x is y plus 2 to y plus 3. We can write probability of 2 less than or equal to x minus y less than or equal to 7 as 0 to 7 y plus 2 to y plus 3 xy 1250 dx dy. This is both are equal. 0 to 3 to 10 integral my x minus 3 to x minus 2 is equal to 0 to 7 x y plus 2 to y plus 3 or gives same probability, only the order of integration changes. One important question: should we use vertical strips or horizontal strips while setting the double integral? In vertical strips method, keep x fixed, y varies from lower boundary to upper boundary, integration is dy dx between, but when the region is naturally described by y is equal to x f of x. In the horizontal strip method, keep y fixed, x varies from the left boundary to the right boundary, integration is the order changes dx dy. First we integrate with respect to x, and then with respect to y. Best when the region is naturally described by x is equal to g of y. The difference between vertical strip and horizontal strip: fix x first, y changes top bottom dy dx. Here fix y, x changes left to right dx dy. Here choose one method that gives simpler limits of integration. Both methods produce the same probability because they represent the same shaded region. From the We evaluate the probability now. From the previous frame, probability of 2 less than or equal to x minus y less than or equal to 3 is integral 0 to 10 integral x minus 3 to x minus 2 xy 1250 dy dx. First integrate with respect to y, then keep x constant. The 1 by 1250 comes out, x is constant here. Take the range of second variable only, x range only 3 to 10 x into y square by 2. We keep this as constant. Integrating integral y gives us y square by 2. X is constant here. The range of y is x minus 3 to x minus 2. Here simply substitute the upper limit, a y square, x minus 2 whole square minus x minus 3 whole square gives us 2x minus 5. So this is 1 by this 2 comes here, multiplies 2 becomes 2500 3 to 10 x 2x minus 5 dx. We have already integrated over dy. So next we need to integrate with respect to x. Here this becomes 2 into x cube minus 3 minus 5 into x square by 3. Simplifying, this becomes 539 by 300 after substituting the values 10 and 3. First we need to substitute upper limit minus lower limit. Here now our answer is probability of 2 less than or equal to x minus y less than or equal to 3 is approximately equal to 0.1797. Here this is approximately an 18% chance that the difference between the two random variable lies between 2 to 3. So I thank ChatGPT for technical collaboration in solving this problem. Thank you. I wish you all the best.